stable or unstable? It's called a stable, it's stable, and it's called a center. So the technical name is a center, and it is stable. I want to now distinguish between stability and asymptotic stability. The two are very different from each other. They do not imply each other. So something may be stable but not asymptotically stable, and vice versa. And what do I mean by this? Again, there are very strict definitions given, but let me do this in pictures. If here's your critical point and you choose some neighborhood of it, then this critical point is said to be asymptotically stable if any initial condition in this neighborhood eventually tends to this critical point. So, tends to. Any initial condition in this neighborhood U of this critical point x bar, if it tends to this critical point asymptotically, then it is said to be an asymptotically stable critical point. On the other hand, if here's a critical point and you have a neighborhood U, any initial condition which is found inside this neighborhood, if it never leaves that neighborhood for the rest of time till t tends to infinity, then it's said to be a stable critical point. Never leaves. This is stable. This is asymptotically stable. I put it to you that this does not imply that, that does not imply this. Well, I mean, in the stable case, it's clear that it need not be asymptotically stable because this fellow could just go round and round. So it's not asymptotically stable. On the other hand, this fellow may do this and come back. So it's not stable. Even then it could not. It should be for an arbitrary neighborhood in the neighborhood of this point. Sufficiently small neighborhood. So it's clear that, okay, this is linked to a very rigorous concept called wandering and non-wandering sets, but I don't want to get into that technicality. But in very simple plain terms, this is all it is. The difference between stability and asymptotic stability. That's why I carefully called these guys asymptotically stable node and asymptotically stable spiral point, whereas this is just stable. The center is stable. It's not asymptotically stable. Now, to anticipate your question, Hamiltonian systems, which are conservative systems, do not have, most of these guys, no nodes are possible. Only saddle points and centers are possible for a Hamiltonian system. The other attractors are not possible, or repellers are not possible, because they will change measure, you will see. Yeah. Doesn't matter. No. As long as the system is ergodic, the Poincare recurrence theorem is valid. Yeah. Yeah. No, if it's not chaotic, no. Even if it's chaotic, then it doesn't matter. No, we'll see. We'll see explicitly. Once the measure is preserved, that's enough. So you cannot have these guys which will change volumes in phase space and so on. Now, one quick thing before we go on to the general case of what's meant by dissipative or conservative system. This thing here tells you immediately that you can classify all these points very conveniently by simply looking at the behavior of T and delta. You don't have to look at A, B, C, D anymore, 4 parameters. Only T and delta are relevant to our system, to our classification. So let's see whether we can do this. I'll plot T here versus delta here. And I'm not going to allow delta equal to 0 because that's degenerate. So this line is forbidden. And let's look at what happens. This is the origin in this t delta space. First of all, this curve t squared equal to 4 delta is a parabola. And inside, t squared is less than 4 delta, and outside t squared is greater than 4. If t squared is greater than 4 delta, this is a real number. And then the eigenvalues are real, both real. And then it will depend on whether t is positive or negative. So it's clear immediately that if delta is negative on this side, then this fellow here, it's guaranteed one of the eigenvalues is positive and one of the eigenvalues is negative. Always. So it immediately implies that throughout here you have saddles. Throughout. And they're all unstable. If t squared is bigger than 4 delta, but delta is positive on this side, this is a real number here, then it's an unstable situation. Therefore, you have unstable, what points? What kind of points? It's a real number, so it's not a spiral, and these are unstable nodes in this region. If t squared is less than 4 delta, but delta is positive, then this thing here is imaginary number, and you have a pair of complex conjugate roots. But t is positive, therefore this is an unstable spiral throughout here. On the other side, it just becomes stable nodes, asymptotically stable nodes, and asymptotically stable spiral. I'm sorry, I'm writing very small. I don't know if you can even see it from there. I couldn't when I was sitting there in the morning. But I presume your eyesight is better than mine. I'll try to write bigger. But this is all asymptotically stable side. That side is unstable. As you cross this line, an asymptotically stable node becomes a spiral. It's like going from overdamped to underdamped through the critical damping region in the oscillator case. What about this line? When t is 0, when t is 0, you have pure imaginary pair of pure imaginary nodes, and these are centers. So periodic motion occurs only here. This is all centers. And it's stable. Now the mathematicians like this sort of figure because you've reduced everything in this simple 2 by 2 case to just looking at the parameter space in 2 effective variables, t and delta, and you know exactly where the system is and what it does. Now, when you have a system with a certain dynamical behavior and you perturb it slightly, you change the parameters slightly, if the nature of the critical point or the flow, overall flow doesn't change, then that kind of behavior is said to be structurally stable by mathematicians. So, saddles are structurally stable. I'm sitting here with some A, B, C, D. I change those parameters a little bit. I expect that things will move around a little bit here. A saddle will remain a saddle. Ditto here and here and here. After all, it may cross this line, but whatever is asymptotically stable remains asymptotically stable. Whatever is unstable remains stable. With just one exception in this picture, and that is if you're on this line, then a small perturbation can move you off this line. And then, if the feedback is positive, the friction constant has a wrong sign, you have an explosive growth. And if it has the right sign, you have damping on this side. The oscillator is sitting here. And if your friction constant has the wrong sign, you're here. If it's the right sign, you're here. So in either case, stability has been replaced either by instability or by asymptotic stability. So a center is structurally unstable. Every center is structurally unstable. But a center implies periodic motion. So periodic motion is structurally unstable. It requires very careful tuning of parameters. The moment you put a little bit of friction, a little bit of dissipation, no more periodic motion. Yeah.
So a center will always imply closed orbits.
A center, yes. A center implies periodic motion, definitely. Purely oscillatory. Purely oscillatory. In this simple example, now if you have higher dimensions, then center manifolds can be very complicated. You have all kinds of behavior.
It will always be closed.
There will be closed orbits around. Yeah.
It's not obvious one.
It's not obvious immediately, but we'll look at the 3-dimensional example. Show you the 4-dimensional example. Yeah.
So how do you call the centers to be structurally unstable?
Because the moment you change the parameter a little bit, it is likely that it moves on this line itself, moves up or down. But that's a set of measure 0. This huge area available, you've got to be exactly on one line. On the other hand, typically it will move here or there. And then whatever was stable has become either unstable or asymptotically stable. No longer periodic motion. Periodic motion is very bad. I mean, to answer this earlier question of about higher dimensions, typically periodic motion would imply that all the dynamical variables come back to their starting points. More typical would be that several of them do, some of them don't with the same time period. And then you have quasi-periodic motion. That's a little less regular than strictly periodic motion. The phase trajectories are not closed, but the system is not mixing. It doesn't have exponential growth or anything like that. It remains in some bounded region of phase space. And that's the next possibility that can happen. And generically, that's what will happen. If I give you two totally unconnected periodic motions, what's the probability that the periods of the two are in some rational ratio? Generically, they would be irrational. And then the motion is not strictly periodic in the full phase space. That's more like what happens. Yeah.
Going back to the stability definition,
Yeah.
can't you always draw a neighborhood in which circular orbits say would leave and then come back?
No, if I choose an arbitrarily small neighborhood, that's not true. That's not true. There must exist an arbitrarily small neighborhood in which this happens, always. And that's not necessarily true. So the fact that periodic motion is extremely structurally unstable, and as you increase the number of dynamical variables, it becomes more and more rare because all the periods in the system, natural periods, must all be commensurate with each other. That is why it is very structurally unstable. That's also the reason, by the way, it's a sort of loose way of saying this, that an extremely regular heartbeat is not good news. not good news. That means that it's too much resonance. Too much resonance, and then it's structurally unstable, it can go off. If you look at a baby's heartbeat, its heartbeat is very complicated. I'm not going to get into arrhythmia here, but people have done studies of it. The most robust heartbeat is that of an infant, a healthy infant, which sometimes, as people have tried, they're squirmy babies, and sometimes they jump off their mother's laps, and sometimes they fall down 1 or 2 floors, and nothing happens to the baby. Look at the shock that the system is going through, apart from the other physical damage, look at the shock going through to the heart. And yet the baby is very robust because the heartbeat is in a strange attractor, which is structurally extremely robust. No matter what you do to it, all the ill treatment doesn't hurt. It still bounces back because the heartbeat is very irregular, but in a very nice way. Irregular, not like somebody who has fibrillation, but in a very robust attractor. It's in a part of phase space, very complicated higher dimensional phase space, where it is very difficult to push it out of that. On the other hand, those who are susceptible to fibrillations and so on are poised on the edge of chaos. They're really poised very delicately, and little perturbations can knock you out and make it unstable, uncontrolled oscillations, and then of course you're finished. So in that sense, this simple two-dimensional example already tells you that periodic motion is structurally unstable. Very, very fragile. Now, as I pointed out already, in higher dimensions, this classification is not so trivial. For example, you could have various kinds of saddle points. You could have saddle points in which you flow in 2 directions, like this, but you flow out in 1 direction, etc., etc. So this is all part of something called index theory, or Morse theory, which classifies some of these critical points. But it becomes a bit of a fool's game because the attractors, the fixed points, critical points in 3 dimensions, there are other attractors coming in. Whereas in 2 dimensions, the only attractors possible are critical points, and dimension 1 attractors called limit cycles. They are isolated periodic orbits. But in 3 or more dimensions, you can have fixed points, critical points. You can also have critical tori. You can have tori or attractors, which are tori, the shape of a torus. But you could also have strange attractors. And you do have strange attractors, which are fractal objects. And in higher dimensions, it gets even worse. So since we don't know how to classify all strange attractors, this is a sort of fool's game. Beyond it is pointless to try to classify critical points. You could do it, but then it's not meaningful, because most of the time nonlinear systems get into strange attractors if they are dissipated. Now, quickly let me dispose of the idea of what's meant by a dissipative system and what's a conservative system. Let me give an operational definition, not that I'm going to adhere to it too strictly, but it's a very simple notion. So let's start with our familiar example. X1 is F1 of X1 to Xn, autonomous system, and I go down up to Xn. Say F of X1 to Xn. Let's consider initial conditions in some volume element in phase space. So little volume element delta V, which is equal to delta X1 up to delta Xn. And ask, how does this volume element change? After all, when it flows, a point here might flow to some point there, when this point here might flow to something here, and the new volume element might look like this. It might look very complicated, it might put out all kinds of tendrils and so on, as will happen typically. But this volume element evolves to some other volume element. And let's find out what's the rate of change of this volume element with respect to time. So d over dt of delta V, this is equal to the time derivative of all these guys. So the first term will be d over dt, delta x1, multiplied by all the other fellows, plus the other terms. I go on differentiating it by the chain rule. And I need an equation for this. Since x1 dot is f1 of all these fellows, it follows that x1 plus delta x1 dot equal to f1 of x1 plus delta x1 x2 up to x. But that's equal to f1 of x1 into xm plus the derivative of this delta x1 at the standard point multiplied by delta x1 to first order. So if I subtract this equation from this, I have d over dt delta x1. I plug that in here, this guy here becomes delta f1 over delta x1 times delta x1 itself. So this immediately becomes equal to delta f1 over delta x1 plus delta 2 delta x2 blah, 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 up to the last term times delta v itself. All the delta x's get multiplied. But what's this equal to? It's the divergence of this vector field with respect to all the phase space variables. So we have this interesting relation which says d over dt of delta v equal to divergence of f times delta. No matter how the shape changes. Yeah.
So delta of x1 dot was equal to del f1 by del x1 into delta x1. Here we have derivative of delta x1.
Yeah. Exactly. Yeah. So delta x1 dot. So what I'm envisaging is this. This is x1. This is x1 plus delta x1. And I'm asking, what's the rate of change at this point? What's the phase space velocity here? The first order in this difference, it's equal to delta f1 over delta x1 times delta x1. So I have this general relation, and now if I say the system is measure preserving, the flow is measure preserving, and the flow is in the measure I take to be the normal volume element in phase space, then del dot f identically equal to 0 would mean that the flow does not change phase space volume. arbitrary delta. And let me call flows where del dot f is identically 0 conservative, and where del dot f is not 0 non-conservative. And we are generally going to be concerned with bounded phase space. Something which becomes exponential simply because the phase space is infinite is not very interesting. It's not true chaos or anything. So in general, dissipative systems would have del dot f less than 0. So things would flow. You could still lose information, because just imagine, look at this picture. In in higher dimensional space, suppose you start with a little ball of initial conditions, and there's exponential separation or loss of information in some direction, this amplification of error in some direction, then even if this ball finally ends up on a line, shrinks from a 3-dimensional object to a 1-dimensional object of this kind, it's possible that these 2 points go here and here, respectively. So the distance between these 2 points can increase to the system size itself, or the size of the phase space that you're interested in. So you could still have loss of information because of this. You could still have amplification of errors, arbitrary amplification of errors, even if it is measure preserved. Because the initial volume element could shrink into a lower dimensional object. And that's what happens in a strange attractor in a dissipative system. Yeah, because I'm going to define dissipation, just the idea that you are friction. The volume contracts. Yeah. The volume contracts. And I'm interested in the rate at which it contracts. And in typically chaotic system, if it flows into a strange attractor, the volume element would contract exponentially. But it would go into a lower dimensional object. It won't go to 0, essentially. It would go to some lower dimensional object. So the volume would be 0. The volume of a line is 0.
For example,
If it, which oscillator? Yeah, in the damped harmonic. Yeah. Yeah, going in. No, going in. I'm not interested in something going on. Goes in. So in the damped harmonic oscillator, this point here would spiral into this origin. This point here would also spiral into the origin. So what's an initial volume element would finally shrink arbitrarily small and then exponentially go to 0. So the dimensionality of this volume element decreases from 2 to 0. Starts with an area and becomes a point. Not in an autonomous system. Not in an autonomous system. What happens typically in dissipative systems like the Lorentz attractor and so on is that in a 3-dimensional phase space, an arbitrary volume element in phase space, which has 3 dimensions, falls, all the points typically fall into what's called a strange attractor, which has a fractal dimension between 2 and 3. It's 2.06. This famous butterfly picture that you see of the Lorentz attractor, that has a fractal dimension of 2.06. Because it's sort of intricately, very complicatedly interwoven. So the topology of it is very weird. It's a fractal object. It looks like 2 planes, but actually it's a little more than that. It's 2.06. But that's certainly less than 3. So the volume of this attractor, the Lebesgue volume, is 0. But its dimensionality is not. Fractal dimensionality, or box counting dimensionality is not. So typically that's what happens. However, this is too restrictive a definition. It's true automatically for Hamiltonian systems, by the way, as all of you know, because in a Hamiltonian system, you have Q dot is delta H over delta P, and P dot is minus delta H over delta Q, and this minus sign is all important because now I can define X to be equal to Q1 to Qn, P1 to Pn, and the gradient del is delta over delta Q1 all the way up to delta over delta Pn. And then del dot F, F is this guy, these components here. Del dot F is identically 0 because I differentiate this with respect to Q and I differentiate this with respect to P, and the two add up and cancel. So this minus sign in between, this twist that occurs in a Hamiltonian dynamics, implies that for a Hamiltonian system, del dot F is identically 0. There's a famous name associated with this theorem. It says volumes are preserved in phase space. It's Liouville's theorem. It follows very trivially from this statement here. It actually follows from something even deeper. It follows from the fact that summation over I, dqi, wedge product dpi, those who know differential geometry, this guy is conserved, this wedge product. And then you go on doing more and more of these wedge products till the last one is this volume element, the n form, and the 2n form. And then that gives you 0 directly. But in simple terms, this is what is the reason for this vanishing of this. And it means, therefore, that the flow in phase space for a Hamiltonian system, and more generally for a conserved system here, is like the flow of an incompressible fluid. Because, as you can see, an incompressible fluid, the continuity equation says delta rho over delta t plus del dot the current equal to 0, and this current is rho times v, density. This rho equal to constant, incompressible, implies del dot v equal to 0. And this is the phase space velocity. This F is the phase space velocity. So this is why they say that a conservative system, the flow in phase space is like that of an incompressible fluid. But as you know, incompressible fluids already have all possible complicated flows. So it's only incompressible. Everything else can happen. There can be eddies, there can be vorticity, there can be turbulence, etc., etc. So all that happens in phase space as well. Just the fact that, yeah. Pardon? It's true for?
Gravity in the equation of motion.
Non-autonomous systems? Well, H is not a constant of the motion in a non-autonomous system, but Hamilton's equations are still valid. So that is still true. There are other invariants, but this is still true. This structure has nothing to do with the Hamiltonian's form at all. It is still true. But I'm not happy with this because it's too restrictive. There could be flows in which you have sort of periodic motion, and in some parts of the periodic orbit, the flow expands, in some parts it contracts. If that happens, then on the average I'd say it's still a conservative system. Right? And there could be changes of variables, and let me give you an example, a very famous example. Let's look at this population example. This is called the Lotka-Volterra problem. Lotka-Volterra model, which I'm sure many of you have seen. It has to do with two species, and one species eats the other. And it was first found in the, I don't know the full history, in the Adriatic Sea. Fishermen found that catches of two species of fish were kind of out of phase with each other by 3 months or something like that. And when one was large, the other was small, and vice versa. And it was kind of periodic, and they wanted to know why. And then Lotka and Volterra came up with this very simple explanation of why, and today it's the basis of all population dynamics. So suppose you have rabbits and foxes, which is easy to understand. The rabbits eat grass, and the foxes eat the rabbits, but are non-vegetarians, pure non-vegetarians. They eat only the rabbits. Then in the absence of any rabbit, of any foxes, the rabbits would of course grow, and grow exponentially. They have some birth rate, so this is equal to some alpha x. X is the population of rabbits, assumed to be large enough so you can write a differential equation. Alpha is some positive number. This of course grows exponentially. Now the foxes, population is y. In the absence of rabbits, these foxes would have a death rate and a birth rate, and since they have no food to eat, they would die down eventually. So this would be some minus beta y. And the phase plot is very simple indeed. We are interested only in the first quadrant, but actually this is valid for all real x and y. So it's clear that one eigenvalue is alpha, one eigenvalue is minus beta. Therefore, the population of foxes dies, the population of rabbits increases. And this is a saddle point. Now we switch on an interaction between these two guys, and the idea is that these foxes would start increasing because they eat rabbits, and these would get depleted because they're eaten by foxes. So there's a negative term minus and some constant. Let me call this gamma so that the matrix looks nice. Minus